All right, welcome back, everyone. So you're gearing up for a major networking exam, right? Whether it's your university finals, the CCNA, or maybe Network Plus, you are in exactly the right place. In this explainer, we're going to tackle the absolute foundation of network communication. We are going to completely master the TCP/IP network access layer. We're going to break this down together by looking at the exact types of tricky questions a professor is pretty much guaranteed to ask you. By the time we're done, you're not just going to be memorizing facts, you're actually going to understand the mechanics of how data physically moves. Okay, let's dive right in.
Here's our game plan for today. First, the network access layer itself. Then, frames and MAC addresses. Next, Ethernet versus Wi-Fi, followed by how network switches work. And finally, we'll wrap up with the encapsulation process explained.
Kicking things off with Section 1, the network access layer. Okay, picture this. You're sitting in the exam hall, and you get hit with this classic high-yield professor question. What is the primary role of the network access layer? It seems simple enough, but getting the wording exactly right is absolutely crucial for full marks. Let's look at the gold star answer.
Here it is. The network access layer is the lowest layer of the TCP/IP model. Its entire job, literally its only purpose, is to prepare data for the physical medium and manage how it's transmitted over a local area network or LAN. The key takeaway here is that while higher layers are stressing about finding the right app or routing data across the globe, this bottom layer only cares about one thing. How do I physically send this chunk of data to the very next device on my local network?
Now, I want you to literally burn the number 4 into your brain. In the TCP/IP model, there are exactly 4 layers: application, transport, internet, and our focus today, the network access layer. It's layer number 1, sitting at the very base of the stack. So if a test question asks how many layers make up the TCP/IP model, your answer is 4. Simple as that.
Moving right along to Section 2, frames and MAC addresses.
So here's the next guaranteed test question. How does data actually travel at this lowest layer, and how do devices physically identify each other? Because, data doesn't just magically float through the air or cables as disorganized text. It needs structure, right?
And that structure is called a frame. Down at the network access layer, data gets packaged up into a frame. Think of it kind of like a highly specific shipping box that's only used for local neighborhood deliveries. Notice how a frame contains the source MAC address, like who sent it, and the destination MAC address, who's supposed to get it, along with the actual data payload and a CRC. Now, CRC stands for Cyclic Redundancy Check, and it's there purely for error checking. If a frame gets messed up by electrical interference on a cable, that CRC is going to catch it.
Now listen up, because professors absolutely love to trap students with this next concept, confusing IP addresses with MAC addresses. Let's clear this up once and for all. An IP address is logical. It lives higher up at the internet layer, and it's used to route your data globally across entirely different networks. It actually changes depending on what network you connect to. A MAC address, though, that is physical. It's permanently burned right into your device's network card at the factory. It is your device's unchanging physical identity on the local network.
Speaking of MAC addresses, here's another highly testable detail. 48. A MAC address is exactly 48 bits long, and it's written out in hexadecimal format. Those weird combinations of numbers and letters separated by colons you've probably spotted in your computer's settings. Definitely jot that down. MAC address, physical, 48 bits, hexadecimal.
All right, Section 3, Ethernet versus Wi-Fi.
The question on your exam is probably going to look something like this. How is physical transmission actually achieved in a local area network? We know this layer handles the physical medium, but what actually are those mediums in a typical home or office?
Well, it generally boils down to 2 heavyweights, Ethernet and Wi-Fi. Ethernet is our wired connection. When you physically click a copper cable from your laptop into a switch, that's Ethernet. Wi-Fi, as we all know, is our wireless tech. It relies on radio waves to beam those frames right through the air. And both of these operate squarely within the network access layer.
To get just a little more technical for a second, at the very end of the line, all your digital data, every single email, streaming video, or exam study guide has to become a physical property. If you're on a copper Ethernet cable, your frames are converted into electrical signals. If you're using fiber optics, that data literally becomes pulses of light. And on Wi-Fi, your frames are translated into radio waves. It's kind of like magic, right up until your connection drops right before you hit submit on a major assignment.
Let's jump into Section 4, how network switches work.
Man, if I had a dime for every time this question showed up on a networking exam, I'd probably be retired on a beach somewhere. How does a switch differ from a hub?
It's a favorite because it really tests if you understand how local traffic is managed.
Let's break it down. A hub is essentially, well, a dumb device. If it gets a frame on one port, it just blindly shouts it out to every single other port. It's noisy, it's inefficient, and it causes network collisions. A switch, however, is a smart device. It actually reads that destination MAC address on the frame, checks its internal MAC table, and securely forwards the frame only to the specific port where the destination device is actually plugged in.
But wait a second, how does your computer know the destination MAC address to begin with? Usually you only know the IP address of the device you're trying to reach. Well, enter ARP, the Address Resolution Protocol. ARP is your essential translator. If your computer needs to send a packet to a local IP address but doesn't have the MAC address to build the frame, it sends out an ARP request. It basically yells out to the network, "Hey, who has this IP address? Send me your MAC address." Once it gets that MAC back, it can finally build the frame. Absolutely massive concept for your exams, so make sure you know it.
Finally, Section 5, the encapsulation process explained.
Let's use a real-world scenario from the study materials to tie everything together. What exactly happens to a piece of data as it travels from your computer screen all the way down to a physical printer, sitting over there on your local network?
Before we trace the actual steps, take a mental screenshot of this table. Seriously, pause and commit this to memory. This is basically your ultimate TCP/IP model cheat sheet. You've got the application layer creating the data, the transport layer making segments, the internet layer making packets, and our layer, the network access layer, putting together frames. And look at where ARP is, sitting right at that boundary, bridging the internet and network access layers.
So back to printing that document. This whole downward journey is called encapsulation. Step 1, your computer generates the print job, which is your application data. Step 2, it gets passed down to the transport layer and wrapped up in a TCP segment so it's delivered reliably. Step 3, it moves down to the internet layer where it's encapsulated in an IP packet with the printer's IP address. Step 4, it hits our network access layer where ARP finds the printer's MAC address and it gets formatted as a frame. And finally, Step 5, that frame is converted into physical bits like electrical signals over a copper cable, sent to the switch and successfully delivered to the printer.
I really love this analogy from the source text because it just perfectly cements how these layers cooperate. Think of the whole thing like a postal service. The IP is the address system, the zip code and the street name. TCP is the tracking system, making sure your package actually arrives in one piece. And the MAC address? That is the physical identity. It's the literal front door of the specific house where that package is being handed off.
And there you have it. You now understand exactly how data physically moves across a local network using frames, MAC addresses, switches, and Ethernet. But I'm going to leave you with a provocative thought. If the network access layer only handles local neighborhood traffic, what happens when you need to send an email to a server sitting halfway across the globe? How do routers move those packets globally across the vast internet? Well, to figure that out, you're going to have to master the internet layer next. Keep studying, keep hammering those core concepts, and you're going to absolutely crush your exams. Thanks for hanging out and learning with me today in this explanator.